Hey Will, how do you determine sequence divergence and convergence?
Oh, let me show you a little something. Into the ineffable is really not that hard. Which graph is moving faster? Check the limit as it approaches infinity. Oh, now you're a master.
To determine the convergence/divergence of a sequence, you need to determine if it's top-heavy, bottom-heavy, or equal degree. To do that, you must use n to the n fable. As you can see, n to the n is the fastest growing slope, or curve. Then it goes factorials, exponentials, polynomials, and logarithms. So, if it is top-heavy, that means it's something that is fast and increases very fast. It's on top of something that is slow, something we consider light. So it is top-heavy. Therefore, the limit as n approaches infinity is infinity. Bottom-heavy means that you have something that increases fast on the bottom. So we consider that heavy and is bottom-heavy. Therefore, the limit as n approaches infinity is 0. If it is equal degree, therefore you have, say, a factorial over a factorial, then the limit as n approaches infinity is the leading coefficient of those two terms over each other.
Okay, so now we're going to do some examples about sequences, divergence or convergence. So the first one is natural log of 3x over 4 to the n. So using the n to the n fable test, we know that the natural log grows the slowest because it's a logarithm, and 4 to the n is an exponential function, so it's going to grow faster than the logarithm, so it's bottom heavy. So knowing that it's bottom heavy, I know that the limit as n approaches infinity is 0. So this would be the limit as n approaches infinity equals 0 because it's bottom heavy. And for the second one, we have n to the n plus 4 to the x over 5n factorial. So using our test again, n to the n grows faster than factorial. So the limit is top heavy. So the limit as n approaches infinity is infinity. And the last one, we have 4 to the x squared plus 3x plus 2x cubed over 10x squared plus 4 plus 2x cubed plus 5x. This function is equal degree because both of the highest exponent is 3. And so to find the limit of this, we do the leading coefficients of the two highest exponents over each other. So this would be 2 over 2. So the limit as n approaches infinity for this function equals 1.
Term test, easier than the rest. If the limit isn't 0, it diverges and you quit. If the limit equals 0, you don't know. Geometric series, common ratio, R. When it comes down to it, these aren't very hard. The best part about these is the sum can be determined. Just use the equation that we already learned. They converge when r's between 0 and 1 greater than 1. You can't get a sum. Telescoping series, you already know it extends. Use partial fraction decomposition. When it telescopes, it always converges. When you see this test, don't get nervous.
I was recording something.
Hello, today we're going to do these 3 examples. This one, I'm going to use the nth term test, and I can tell because I can easily take the limit of this. As you can see, this is e to the 3n versus e to the 2n. The log grows very slow, and it's not important. So we can consider this a sub n. So the limit, as n approaches infinity, of a sub n equals infinity because e to the 3n grows faster than e to the 2n, therefore it's top heavy. If it's top heavy and the limit is infinity, that means it is not 0. Therefore, based on the test right here, it diverges by the nth term test. Alright, the next one I can tell that this is a geometric series because I have 3 to the n over 2 to the n, and I can rewrite it like this. Three halves to the nth power. This I can easily see what the common ratio is. The common ratio equals 3 halves, as it is raised to the nth power. Now, to determine if it converges or diverges, we need to look at the geometric series test, and we see that r is greater or equal to 1. Also, make sure to do the absolute value of r. So therefore, this series diverges also by the geometric series test. Right, this final one I can tell is a telescoping series because of the way it looks, and I mean, I don't know exactly, but I can test it and figure out by writing out the first few terms of the series. So to do this, I plug in 1 for n, then I plug in 2, and because it's a sum, I have to add each of those terms. So I have 1 minus 1/2 plus 1/2 minus 1/3. So as I can see, almost immediately, sometimes it doesn't come as quick, these cancel out, the 1/2 and the plus. Therefore, this converges because you get an answer right here, and it is a telescoping series.
Integral test, you already know. Take the integral of the series to know its convergence. If you get infinity, that thing diverges. P series test, it's actually quite simple. Sum of 1 to infinity of 1 over into the p. When I use this test, 85 plus cup, looking at me. P is always positive, that's how it has to be.
Hey guys, time to do some examples. So for the first one, you can see that you can easily convert this into an integral because you know 1 over the x equals natural log of x. So I'm going to go ahead and change it into an integral. So 1 over x plus 1 from 1 to infinity. And because this is an improper integral, I have to take the limit as in, or b, approaches infinity of 1 to b of 1 over x plus 1 dx. Forgot the dx there. So now that I've done that, I can go ahead and take the integral of the inside of the integrand. So I'm going to use u substitution to this because I can't take the integral of 1 over x plus 1 by itself. So u equals x plus 1, and then I take the derivative of both sides. So this equals 1 dx, which cancels out with this dx and subbing for du. So now I have the limit as b approaches infinity for 1 to b of 1 over u du. And 1 over u du, the integral of that is the natural log of u. So I now have the limit as b approaches infinity for the natural log, and I know that u is equal to x plus 1, so I'm going to go ahead and plug that back in. So x plus 1 from 1 to b, and then I'm going to plug in my bounds because it's a definite interval, so limit as b approaches infinity for the limit of b plus 1 minus the natural log of 2. So I'm going to do this one first. So the limit as b approaches infinity, so I'm going to plug in an infinity for b, so this would be the natural log of infinity, which is equal to infinity minus the natural log of 2, but the natural log of 2 doesn't matter because I've already gotten an infinite sum. So the limit as b, well actually, the series diverges because the integral equals infinity. So it diverges by integral test. And for the second one, this is a p-series test. So I can convert the series to look like a p-series, which is 1 over p. So I can have 3 over n to the 4th because to a negative exponent means that it needs to be moved to the bottom of the fraction. So the sum of this, I can do p-series test. So p is equal to 4, which is greater than 1. Therefore, the series converges by p-series test.
Direct comparison is what we're about to do. Don't worry though, it's nothing new. A sub n, b sub n. Determine where they converge. You won't see your grade submerge. Limit comparison. A sub n over b sub n. Yeah, if the limit goes to infinity, it never ends.
Today we're going to do some comparison examples. For this first one, we're going to do direct comparison, because we can obviously see a sub n equals 1 over 1 plus 3 to the n, and b sub n equals 1 over 3 to the n. Now we can easily see that this is a geometric series, and because r equals 3, or r equals 1/3, my bad, and 1/3 is between 0 and 1, this therefore converges by geometric series test. The geometric series. So now on to the comparison part, in which we have a sub n. And because there's this 1 plus right here, this will always be less than b sub n. And because a sub n is less than b sub n, a sub n therefore converges by the direct comparison test. Alright, now on to this one. This one we're going to do limit comparison. So we have a sub n equals 1 over 3n squared minus 4n plus 5, and b sub n equals 1 over n squared. So we just take the highest degree and we just put it over 1, just like in this. So now, to do the limit comparison, all you have to do is limit as n approaches infinity of 1 of a sub n over b sub n. So we have 1 over 3 n squared minus 4 to the n plus 5 over 1 over n squared. So we can rearrange that to be the limit as n approaches infinity of, so we have 3n squared minus 4 to the n plus 5 divided by, which is the same as multiplying by n squared. So this can be rewritten like this, which I can rewrite down. And we can see that the limit as n approaches infinity equals 1/3, which equals a number. Therefore, this converges by limit comparison.
Which is a number greater than 0.
Plus then minus, plus again, minus 1 more, and we always win. Alternating series goes up and down. Don't forget the remainder. You don't have to round.
Hey guys, let's do some alternating series. So, to start, I'm going to figure out the convergence or divergence of this series. So, I know it's alternating because of the negative 1 to the n. So, I'm going to start by writing out a sub n. So, a sub n equals 1 over n. And if I do a sub n plus 1, I have 1 over n plus 1. And because the denominator is bigger on this one, this would be a smaller fraction than this one. So that way I would know a sub n plus 1 is less than a sub n, which is the first part of the test. And then I would do the limit as n approaches infinity for a sub n. And because this is a bottom-heavy fraction, and as n approaches infinity, the limit would equal 0, which is the second part of the fraction. Therefore, the series converges by alternating series. And the second part is the remainder error example. So I'm given this problem, and I know that the sum of this series is 2/3. So using that, I went ahead and wrote out all the terms or a couple of the terms for the sequence. So it tells me that I have to have an error less than 1 over 100. So I wrote out the terms until I got to a fraction that was less than the fraction 1 over 100, which was 1 over 128. And I added the terms before this number up, and I got 43 over 64. So using the formula, R7 is less than or equal to the first neglected term, which is a sub n plus 1. So using this, I know that the sum minus, so I could use 2/3 since they gave me the sum. 2/3 minus 43 over 64 is equal to 1 over 192, which equals the remainder. And so this remainder is less than or equal to the first neglected term, which was 1 over 128. So this question is actually asking me to determine the number of terms that it requires it to approximate, so I just count the terms before 128. So 1 plus 1, or 1, 2, 3, 4, 5, 6, 7. So it would be 7 terms.
Ratio test is really quite simple. Might even use it in another unit. If the limit equals 1, you know it's inconclusive. On to the root test, yeah, it's our favorite. Everything to the n power, then you can use it. We got a summary sheet, just make sure you don't lose it.
Now you are.
Alright, we're going to do some examples now. Here's our first example. We're going to use the ratio test. So to do the ratio test, you need to set up a limit, in which you do n approaches infinity of 1, e to the n plus 1. You always have to put plus 1 on the ends over n plus 1 factorial over the original a sub n, which is just e to the n over n factorial. And you make sure you put an absolute value. So then we can simplify this to n as n approaches infinity of e to the n plus 1 n factorial e to the n plus 1 factorial. We can simplify this further, make it limit as n approaches infinity of e to the n plus 1 over e to the n plus 1. Then, keep simplifying. Limit as n approaches infinity of e to the n, or no, e, because you can cancel these out, over n plus 1. And we can easily see that the limit as this approaches equals 0, which is less than 1. Therefore, the series converges by the ratio test. Alright, on to the next one. So this one we're going to do the root test because everything is raised to the nth power, so it would be simple. So you have to do the limit as n approaches infinity of to the nth root of n plus 1 over n to n plus 1. So this simplifies to be limit as n approaches infinity of n plus 1 over 2n plus 1, which is 2n plus 1, which is simple, which equals 1/2, which is also less than 1, and they have the same sort of thing. So therefore this series converges as well, but by the root test.